So let's pick up right here where we left off, namely that we have independent-ish. So what's happening is that, yes, when you take a scoop out of this large box, it affects what's left for everybody else to scoop, which automatically means it's not independent. However, you're taking such a small scoop in relation to the number of beads in the entire box that it's close enough. You're not really having that big of an effect on it, right? So since you're not going to have that big of an effect, we'll just say it's approximately independent, right? As long as your scoop, as long as your sample is less than 5% of your total number in your box, right? So as long as you're taking a small enough sample that you're not going to greatly affect what's left for everybody else, then we'll say it's independent-ish, right? Now, independence is a big deal for us because we've seen it before, right? Well, let me bring up those notes. Right. Chapter 6, binomial, remember? And one of the important things about binomial, right there, number 2, is that the trials are independent. Right. Okay, so we want independence because if we have independence, then we can have the binomial. And then if we have the binomial, then we can approximate it with the normal distribution and life will be grand. Okay, so we need independence, and we're getting that from that top phrase right there, that 4 simple random sample. You need your sample size n to be less than 5% of capital N. That ensures the independence part. Then you get down here to the first bullet. The shape of the distribution is approximately normal as long as n times p times 1 minus p is greater than 10. Now you've seen that before too. That was the last page of chapter 6 right here. If you take a large enough n, look what happens. Look, this was skewed right, because p was 0.2. But if you take a big enough n, then it becomes approximately normal. Aha, right here. N times p times 1 minus p has to be bigger than 10. If it is, then it's roughly normal, normal-ish, if you will. And that means we'll be able to use norm dist, and all that other good stuff. Okay, so this first phrase right here ensures independence. The second phrase right here ensures normality. Matter of fact, hold on, let me pause and label that. There we go. So that top phrase does the independence part. The first bullet right here does the normal part that we saw at the very end of chapter 6. Then the mean, which is the center, will be mu of the p hats, the mean of the p hats. Not the mean of the x bars, that was 8,1, but the mean of the p hats, that's 8,2, and that'll be p, the true proportion of red beads in the box, or the true proportion that's going to vote for so-and-so, right? And then down here, the spread, right? Now, all of this is a pretty ugly box, so you better put it right on your note sheet, right? No need to memorize it, you just have to know how to apply it. And these calculations right here, like for example, if I gave you p, you should be able to find this with just a calculator, right? All right, so let's do an example. According to a recent article, 98% of the people who travel on the New Jersey Turnpike exceed the 60-mile-per-hour speed limit. Law enforcement officials are planning to covertly measure, covertly meaning on the sly, the speed of 750 cars on the turnpike and will compute the proportion of drivers who exceed the posted speed limit. Okay. First of all, do we have independence? Yes, because 750 is well below. The New Jersey Turnpike has a lot of cars on there. So 750 is well below 5% of the cars there. Okay, so that shouldn't be a problem. A lot of the times, by the way, that whole bit right here with the 0.05, a lot of time that's kind of hand wavy, like a magician. You just wave your hands and say, ta-da! And this is one of those cases because we don't know how big the population size is, but we know it's really freaking large. And therefore, we're not going to worry about our 750 being too big, right? It's not too big of a scoop. And I'm going to keep referring back to that scoop thing. We're going to keep using it in chapter 9 and 10 as well. So that bead box, it's a big deal, right? It's laying the foundations for us here. So I wasn't just making it up. All right, so now the shape is normal. Now we need to know that. You can't just say normal. If you're on an exam, you have to say normal and explain why. So the proof of that is that n times p times 1 minus p, that's 750 times 0.98 times 0.02, that's equal to 14.7, which is greater than 10. Okay? All right, so, and again, you could use Excel or whatever to calculate. As a matter of fact, we're going to need Excel anyway, so I might as well give ourselves another problem here. So I'm going to put this as 8.2 example 1, I believe. Yep, example 1. Okay, so let me take a moment here and give us some thoughts. So we know the shape is normal, but let's prove it. Shape normal, question mark. All right, so let's prove it. N was equal to 750 times, actually, you know what? Let's solve some problems for ourselves because we're going to need these numbers later on anyway. So let's do this. N was 750. P was the one they said in the article was 0.98, right? And do we need anything else right this second? I don't think we do. Okay, so to prove it's normal, let's do this right now. So we need n times p times 1 minus p. So I suppose I could take the trouble to find 1 minus p. It doesn't hurt. Equals 1 minus that value. All right, so n times p times 1 minus p is equal to that cell times that cell times that cell. Boom, 14.7, larger than 10. So yes, right? We've got normal. Life is good. Okay, next. And again, we didn't have to do that in Excel. We could have just used a calculator or whatever. But I'm setting up some stuff for later on in the problem. So I figured I might as well get it done and over with. Okay. So here we are. I'm going to need the center and the spread. So the center, according to this little blue box, is the P. So I'm just going to put that down here. Center is mu P, which is equal to P, 0.98. Now the spread, that's much harder to come by. Type equal square root, and this is how you do it in a calculator too. And then you got to tell it P, which is 0.98, times 0.02 divided by N, which was 750. Enter. You get 0.005112 and some change. All right, so there's our shape, our center, and our spread. And that's what we put in right here. Shape, center, spread. When they want us to talk about the distribution, we're going to need to know those things, right? They didn't ask any of it yet, but we might as well. Now, they did ask, what is the minimum number of, technically, cars that should be pulled in order to ensure that this is normal? Okay, so remember that normal is n times p times 1 minus p has to be bigger than 10, right? Okay, but what they're saying is, what is the minimum number of cars, i.e. what is n? So you leave n as a variable, n, but you put in 0.98 and 1 minus 0.98, which is 0.02. Okay, now if you multiply 0.98 times 0.02, you'll get 0.0196 right there. Here, I'll open it up. Hold on one sec. There we go. So 0.0196, that's these two numbers multiplied, and you don't need Excel or any of that. This is just algebra, right? So now if you want to solve for n, like you do, because it said how many, so we divide both sides by 0.0196, which means n is greater than 10 over 0.0196, which is 510.2. You must round up. You can't go any lower than 510.2. If you go any lower than that, you won't have normal. You won't be bigger than 10. So we have to round this up no matter what to 511. And that's what I wrote right here. We must round up no matter what, period. All right. Now, in a random sample of 750 drivers, what is the probability that more than 98.5% of them are speeding? Okay. So let's figure this out. This is example part B. I didn't really have to do A in Excel, so I'm not going to. I mean, that's just simple, straight up algebra. All right, so for this one, they're telling us the P hat is equal to 0.985, right? 98.5%. So we're going to find this two ways. You know this is coming. We're going to find it with StatCrunch, and we're going to find it with Excel. Now, I just happen to have StatCrunch still open, but if you didn't, go to StatCrunch, go to Stat, go to Normal, or Calculators, excuse me, Normal, like that. All right, so I've got it up right here. So I'm going to make this, now this was 0.98, right? Now our standard error is really small, and I'm going to type in lots of decimal places in here. 0.005112077. Okay? All right. If you don't, here, you know what? You don't have to. You can say, like, just type in, 5 decimal places or so, but you want to give yourself several. All right, then I want the probability that x is, now this is a greater than, so I want the arrow going to the right, and then I want 0.985. Compute. And there you go. It tells us it's 0.163. So I'm going to take a snapshot and I'm going to go label this thing 8.2 example 1b export. Fine. There it is. Copy. Paste. Cool. All right, so they can see StatCrunch says the probability that p hat is greater than 0.985 is equal to 0.163, 392007. Okay, so there's StatCrunch. Now, what about Excel? How would Excel do this? Well, remember, Excel doesn't find the right area very easily. It finds the probability that p hat is less than 0.985. Oops, I typed that wrong. Must have my numbers in the wrong place. 985. There we go. All right, so it finds that easily with norm dist. You go equal norm dist. Now it helps if you have your values already typed in. So you can say, okay, I want 985, comma, my mean is 0.98, comma, my standard deviation is this ugly thing, 0.005, blah, 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 comma, true. Enter. Okay, now that's not what we wanted. That's the white side, right? Because Excel, the norm dist function only finds left area. So then we take it away from 1 to find what we were actually looking for. It's equal to 1 minus that value. And there it is. Now notice they're a little bit different from each other. Right, because what happened was I rounded. See how I rounded 0.00511? But down on this one, I left 0.005112077. And you can see it's slightly altering the probabilities, right? So you want to be very careful with these, right? If all else fails and you don't know what you're doing wrong, maybe go back and try giving yourself more decimal places or less decimal places, see if that'll get you the right answer. All right, so there we go, close enough, 0.1640. And then I'm going to paste in that lovely picture we have from StatCrunch. I don't really need the calculator part, I just need that picture because that's the shape of what's happening for this problem. All right, let's stop there. We only have one page left, but I don't want to rush it, and I don't think I have enough time to finish. So I'll see you back here to finish up this problem for the turnpike drivers. See you then.